So, in the 11.5 exercises, you have to plot graphs of polar equations. Remember I've been saying try to draw a picture? That's what he's saying now. For the first 20, he's saying draw a picture. And notice he says by hand. You guys, to graph any of these on a graphing calculator is easy, right? But he wants you to take your time and do it by hand, which I'll do. I'd say you do both. You have the paper out to do things by hand, but you also have the graphing calculator ready. Okay? So let me move this over to the side so that you can see your calculator. All right, talk to me, guys. What mode should I be in? Better be in radians. And you got to make sure that you're in polar mode. Okay? And I'm going to press the y equals here. And notice what it says we're going to graph today. They name these shapes. Now a circle, I could graph that in rectangular coordinates. X squared plus y squared is r squared. But these other ones, yeah, maybe not. Do you have a particular shape you want to see? Are you curious?
Do rose.
All right. Let's do 6. Problem 6, a rose. All right. So what's that look like? Cosine of 5 theta. Let's graph it. Well, that doesn't look very much like, it looks like a squiggle. You can't even see it. What am I going to do? Let's zoom in. All right, let's try again. We're going to zoom in, and let's see if it really looks like a rose. Well, now we're getting there.
What zoom did you do?
I pressed zoom in. Zoom in. You know, I'm going to do one more thing. Now that I'm zoomed in, I'm going to press zoom square to make it look like real graph paper. And it's starting to, does it look like a rose to you? I don't know. I'll press zoom in again. Choice 2. You see it? Now what the heck did it do? Let's see if we can figure out what's going on. And again, drawing by hand, you might be able to see where the rose comes from. So I'm going to give some advice here, okay? You know, when you plot x and y coordinates, I'm sure you do x first and then y. But if I'm given a point r comma theta, what I say you should do is plot theta first. We can't really see that because I moved the thing. In other words, aim, then plot R, fire. You have to aim before you fire. See, R tells me how far you're going to be shooting the gun. The gun is at the origin. And theta is the angle that I need, okay? So let me see. We're going to plot the equation we said was number 6. R equals, what is it? The cosine of, help me out again. 5 theta, okay. So watch how this works. We need a value of theta first. And then we need a value of R, which is the cosine of 5 theta. And what I'm going to do is I'm going to, remember back in the day we used to pick x values and y values. Well, I'm going to pick a theta value. So when I start, I like to start with 0. When I pick theta is 0, that means I'm aiming in this direction, right? That's a 0, that's an angle of 0 radians. Okay? And now I'll compute R equals the cosine of 0, which is what? 1. And so how far out do I want to go? Well, I want to go out to a distance of 1. So if I gave you the xy coordinates, they'd be 1 comma 0, right? I'll put them in little brackets like this so you could tell them apart. How about that? So that's 1 comma 0. But r here is 1 and theta is 0. Okay, time for another value of theta. Can you give me a good value of theta? Any number. 1's okay. Remember that theta is in radians. So give me a better number. I like pi, right? Now I'm going to put pi way, way, way down here. On my chart. Because to get r, remember what I'm going to do is I'm going to do the cosine of 5 pi. And what's the cosine of 5 pi? Thanks, guys. Yeah, we did memorize the unit circle.
Oh, -1.
Thank you. I know you got to go around a few flips, right? -1, right? So what does that mean? That means when the gun is aiming in the pi direction, now which way is that? This way we're going to aim, right? When we fire, we're going to have an R of -1. Where's it going to end up? Right here. Because it's aiming this way, but we fire backwards. Isn't that strange? That was too fast. All right, let me try a value between 0 and pi that might be more interesting. And you're going to say, why'd you pick this? But I think I might be able to make some sense. Tell you what, I'm going to skip a line here, and right here, I'm going to put pi over 5. Pi over 5. Now, pi over 5 is not something I'm very familiar with, but for this problem, it actually works out okay. How come? Because what's 5 times pi over 5? We're taking the cosine of pi, which is -1 again. All right? So when we aim at pi over 5, we're going to have an output of -1. All right, let me show it. Let's see. Pi over 5. What's 180 divided by 5? 36. All right. So I'm aiming up here at 36, right? But where am I going to shoot it at? -1. It's going to end up back over here. So this point corresponds to that. Now, if you had to, guys, could you get the x and y values for that point? Yes. Would it be hard to do? Yes. That's what our homework's been on. I don't want to. I just want to start understanding that I aim one direction, that's my theta, but the r is back over here. This is tricky. Here, let's suppose that I use a smaller value. What would happen if I put in pi over 10? Pi over 10. What does r equal? Cosine of pi over 2. What's the cosine of pi over 2? 0. That's weird. So that's kind of strange. I'm going to aim in between these two when I do pi over 10, but the output is 0 right at the origin. That's really strange. I'm going to show one more, and I'm going to show it in red. Pi over 20. You guys, what's the cosine of 5 pi over 20? Well, that's the same as the cosine of pi over 4. And isn't that square root of 2 over 2? Yeah? Is square root of 2 over 2 bigger or smaller than 1? Smaller. That means when I aim in between these two, the output is not quite as big as 1. All right. So I'm going to show you what happens. The gun starts out aiming at 0. A 0 degree angle, so it's aiming at this point, 1, 0. as the gun begins to rotate through the angles, it's going to get to pi over 20 next. We trace out this piece of the curve. By the time we get to pi over 10, my radius is now 0. And so I'm going to get to the origin. By the time I get to pi over 5, we're going to have rotated farther and be in the negatives, and so I'm going to be here. And then what happens is it's going to rotate farther. And how many of you are familiar with spirograph? No? Wow, I just dated myself. A little toy we used to play with. All right. Never mind. Wow. I haven't taught trig in 4 years, and it shows. All right, so let's see. But back to here. You know, let me zoom out again just for a minute. I want you to see as this graphs the order it does things. Here, I'll zoom in again. And one thing you do is when you graph it, if you press enter as it's graphing, you can pause the graph. And this is actually worth to see. Freeze. Oh, it didn't do it. Man, I wasn't quick enough. Oh, actually, it paused now. That's funny. All right, I just wasn't quick enough. One thing nice about your calculators is that they don't have a computer processor like mine, so they go a lot slower. Oh, look at that. You can't see anything when I zoom in that fast. We'll try again. Zoom out, and I'm going to try and pause it. There. Do you see what it did so far? It graphed. So the pointer, we started out aiming at 0. We ended up, by the time we got to pi over 20, the radius was 0. By the time we were aiming at pi over 10, I say pi over 5, up here somewhere, 36 degrees, r was -1 down here. And then it's going to go back in. Now, by the way, you see where my arrowhead is? The white arrow? Right up here. What angle is that? We haven't done that one yet. That's pi over 2. Let me compute that one. So again, we're not at pi yet. Pi over 2 cosine of, what's 5 pi over 2 going to give me? Well, that's the same as the cosine of pi over 2, right? So that's going to be 0. And so what that says is, by the time the graph gets to pi over 2, I should be back at the origin again. Okay? I paused it before that happened. But what we should see is the curve should come down to the origin and then go through it again, because now it'll have negative r's. So let me go ahead and finish it up. You see that? Now, by the time we get to pi, we mentioned that the radius is -1. And so that means by the time we get to pi, the curve closes up, because it's aiming this way, but -1 goes that way. So really, the entire curve, you saw it graph, but you get a 5-leafed rose from this picture. And the funny thing about this curve, I mean, we see curves like this in our lives, but to try and model this with x and y coordinates would be very challenging. But you can do it with an equation. You guys have questions so far? Hey, does it say I have to sketch these by hand? No. Let's use the technology. All right. R equals 3 cosine theta, and R equals sine theta. And you know what's funny? Is that it may not have happened yet, but it's going to happen. You're going to get to a point where you actually know what shape these things are. Kind of like you know y equals mx plus b is a line. Tyler's dreaming about it. He's so excited. All right. But anyways, let's see if we can get through this, right? So let's go ahead and put them in your calculator, and we'll take a look, and then I'll go from there. So we don't need the rows anymore. So let's see. I have 3 cosine theta, and I have sine of theta, and I'm going to put them both on the same picture. See what it looks like. Well, I sure don't see very much. Oh, I know why. Because I'm zoomed in so much. Let me hit zoom standard. That's probably what yours is going to look like. Oh. Well, I can zoom in from there. You're going to have to play with the window a little bit until you figure out what these graphs really look like. And remember that if you ever want a better picture once you're zoomed where you want to, you can hit zoom square and make it regular old graph paper. What shape are these things, you guys? Circles. I should have known that. Because if I do this, for instance, r squared equals 3r cosine theta. R cosine theta is the same as what? So this is just 3x. And over here, r squared is the same as what?
Squared plus y squared.
X squared plus y squared. And if you kept going, you could get it to say x squared plus y squared equals r squared. You'd have to do some completing the square. I showed that last time. I don't want to do it now. What I want to do instead is say, do these circles intersect? Yeah. Yes, they do. Now, how do we figure out where points of intersection are?
You solve them algebraically.
Exactly. Just like you did back when you did 2 lines and you want to know where they intersect. I mean, we graphed 2 lines and we looked, but that was hard. But you can do the same tricks that you did in algebra class. Here's the thing. If r equals 3 cosine theta and r equals sine theta, you can substitute in for r. So what happens is I can write, let's see, 3 cosine theta equals sine of theta. Ooh, now what? Well, now there's only one variable. And the only variable is what? So we just have to figure out what theta is. Ideas of what to do next? Yeah, Liza? That's what I would do. Divide both sides by cosine theta. And so now the equation is, well, tangent of, let me write it here. Tangent of theta is equal to what? 3. And isn't this just like the problems we were just doing, right? Tangent of theta equals 3. So let's see, where does that happen? Well, lots of places, right? So one solution would be theta is arctan of 3. That's one solution. There are other solutions, perhaps. Okay? And so here's where I think the picture can help. As I look here at my graph, how many solutions do you think I should get?
2.
I agree, we should get 2 solutions. Now one of them, it says, is arctangent of 3. Okay? And by the way, does my calculator do some nice things here? Let's see. Second calculate. It'll calculate a value. Well, let me do that. Enter. Notice it doesn't say x equals, it says theta equals. So let's put our theta in. What's our theta? Arctan of 3. And I'm in radians, so hopefully this will work. Did it work? There it is. It even gives you the x and y coordinates, which is kind of cool. Okay? So we found one of the solution right there. Now what about the other solution? Where's the other solution does it look like? The origin. So here's the deal. we have to check, is the origin a solution? And if you read the examples in the book, Dr. Stitz calls the origin, it's sometimes called the pole. Like the North Pole or something like that. Is the origin a solution? And the only way you can ever be at the origin in polar coordinates is if r equals what? 0. So basically what we're really checking, when I say we're checking is that a solution, basically we're going to say, is r equals 0 a solution? Okay? And you wouldn't find that by eliminating r, because you wouldn't know what r equals. So basically you kind of look and you say, 3 cosine theta, does that go through 0? Can you think of a theta you can put in which will make r equal to 0? Let's try that. Cosine of theta equals 0. Does that ever happen?
Oh, cosine of pi over 2 or something.
Cosine of pi over 2? Or what else? 3 pi over 2, right? There's a lot of ones, right? So you can get solutions that way. And what about sine? Sine of theta equals 0. Where does that happen?
0.
0, pi, 2 pi. But the point is that, yes, they both happen. Okay? So is the origin a solution? You guys are going to have to check that separately. Does that make sense to people? Very good. Okay.